In this problem, we have two photons with an energy E. They collide at an angle theta and create a particle of mass m. And we need to figure out what is m. There's two ways to solve this problem. The first way, which is what I prefer, is with a balance of just the four momenta using four vectors. The second method uses the traditional energy and momentum balance. The four momenta of each of the photons is given by P equals the energy divided by C. The momentum of each photon, which happens to also be E over C, but since it's in the x component, we have cosine of theta over 2. And the y component, it can either be positive or negative, so we have plus or minus E over C sine of theta over 2. There's no momentum in the z direction, so I'll just ignore it for now. Now the total momentum is equal to the sum of the two four momentas of the two photons. So we simply double each term, 2e over c, 2e over c cosine of theta over 2. But this term would be 0 since the net y component of the momentum is 0. Here we can exploit a very useful symmetry when dealing with four vectors. That is, the square of the four momenta is an invariant, and to be more specific, it's equal to mc squared. That is, once all the momentum gets transferred to the mass m. And by taking the dot product with itself, we can express this as 2e over c squared minus 2e over c cosine of theta over 2 squared 2. Now we just have to isolate and solve for m. And isolating for m and taking the square root of both sides, we get 2e over c squared times the square root of 1 minus cosine squared of theta over 2. But we can use Pythagorean's theorem to simplify this to be sine squared of theta over 2, or 2e over c squared sine of theta over 2. And that's our expression for the mass. We can try solving this the traditional way, where we have conservation of energy and conservation of momentum separately. Conservation of energy would give us 2e equals the relativistic energy of the mass, m gamma mc squared, where gamma is the Lorentz factor. Now, if we are able to figure out what this Lorentz factor is, and we can do that by figuring out the speed, then we can just isolate straight away and solve for m. So we need a separate equation, and it's the conservation of momentum. Here we have the x component of its momentum in the horizontal direction. We have e over c cos of theta over 2 as before, and since there's two photons, we'll double this quantity. And it's going to be equal to the relativistic momentum formula, gamma mv. But notice that we know what 2e is already. It's just gamma mc squared. So we can rewrite this by substituting in gamma mc squared over c cosine of theta over 2. We can find an expression for, my bad, that's supposed to be capital M, that's supposed to be a capital M. We can find an expression for v. Gamma m cancels out, gamma m cancels out, and one of the powers of c cancels out. So we get v equals c times cosine of theta over 2. Now, back to our original energy equation, we can isolate for m to get m equals 2e over c squared times 1 over gamma. And 1 over gamma is given by the square root of 1 minus c squared cosine squared theta over 2. That comes from v squared there, over c squared. The c squareds cancel out, and you can see we have, like last time, sine of theta over 2. So again, we have mass is equal to 2e over c squared times sine of theta over 2. And I highly recommend you to double check the limits to see if it makes sense for critical cases where theta is equal to 0 degrees, 180 degrees, and so forth.